How are you? Sorry?
Slides are so I
Yes. I was just listening. So pull back all the slides.
He might be an ancient fish. This huge debate going on.
более сильная, чем и вот для плановой техники на мир перенести уверенным счетчиком.
Right. Good afternoon, everybody. Sorry, I was waiting for the chair's place in the wrong room, so that's why I'm a bit late. But let's get started because we don't have enough time. Right. So I hope you're here for the Cfrg meeting. We only have an hour. We're the last session, so hopefully we can, if we're a bit late, we can stay a little bit longer, but not for very long. Okay. So, no? Right. Thank you. So I hope you've seen all the note well by this time. We have a note taker. Anybody wants to lurk in Jabber room and just come back to the mic if there are any questions? Should be the. Oh, thank you, Stephen. So I'm one half of the Cfrg co-chairs. Kenny cannot be here. You might have heard that we will be looking for a third co-chair to help us with the load. Quickly, so there was a request to move one of the hashing to curve to be the first presentation because of a conflict. So I've updated the agenda for this. Any other agenda bashing? It doesn't help that I don't actually have a slide with agenda. So right. Quickly, document status. We have 2 RFCs since London. Update to Charchat 20 and Poly 1305 and XMSS. No documents in RFC editors queue. There are 5 documents waiting for document shepherds. For one, Paul Hoffman volunteered to help progress hash-based signature. Thank you to him. So we are trying to figure out with Ellison what the process is going to be for a shepherd who is not research group chair, but I'm sure we can make tools work with that. There was a bit of a backlog, and this was waiting for me and Kenny to review various documents. I think I reviewed 3 out of 4, sent comment on Argon 2, and I will be sending comments on the other 2 shortly.
So the question in Jabber is, what about the PKEX draft?
Yes, I need to follow up on this. I also got requests to progress aspect 2, so I'll be trying to deal with this shortly after the Montreal. We have several documents active, VRF, hash to curves, randomness improvements, and transition to quantum. I think that's it. Okay, so. Okay, let's get started with the first presentation. Yes. What this? Yeah.
All right, hi everyone. My name is Chris Wood. I'm going to be talking to you about our draft hashing to elliptic curves. Just a quick update because we're mostly trying to work through the many outstanding to-dos we had in the first revision that was submitted, and now we're in a good state where we can actually start, iterating on it within the research group. So some quick background on this. The main goal of this was to sort of go through and survey all the different algorithms that you could use to hash to elliptic curves that were spread throughout the literature and used in many different particular applications, PAKES being one of the primary use case here, and just write them down so it's easy for implementers to actually get it right and correct and so on and so forth. So after London, the initial version was adopted, and it contained a couple issues that were pointed out on the list thereafter. In particular, it convoluted some terms like encoding, serializing, and hashing. It sort of just said everything was hashing, and that's not the case. So we took some time to decouple these terms and make it more precise. And it came with 3 detailed algorithms and accompanying stage implementations of an outstanding to do. And we have filled that to do in the latest version. So the main updates are as follows. like I said, we separated encoding, serialization, and the random oracle instantiation, which is essentially the hashing to curve functionality. And now there's two sections in the document, one for map to curve, which is the deterministic encoding function, and the other for hash to curve, which is the random oracle functionality, which is required depending on your application. We refactored the algorithm recommendation table such that it's clear, or we hope that it's clear if you have a particular use case for a particular application for a particular curve, which algorithm you should use. Of course, we're open to recommendations or suggestions for improving that particular table in that format, and also the recommendations in general. I think once we get everything nailed down and the algorithms actually fleshed out, the recommendations may likely change. And we also took an action last time to work with Karthik and the people in the HackSpec team to create implementations of each map to curve algorithm. So now the appendix contain these, and we're trying to help drive that effort forward, because I don't know how much you recall from the last meeting. HackSpec is just basically attempt to create a language to produce formally verified cryptographic implementations, and we thought this was a good candidate to sort of prototype that particular technology, and it's worked out well. We found some bugs in the actual HackSpec library, but all in all, it compiles and runs, and it's pretty great. So just a quick overview on these particular changes. Like I was saying, the map to curve functionality, which has its own dedicated section, is, as I said earlier, basically a function that takes an arbitrary input and deterministic and maps it to a point on a curve. And the algorithms which we include are the same as last time: Ecart, SW. I will not remember the names, so bear with me. The simplified SW that works for specific curves, and then Alligator 2. And then we have a dedicated section for the hash to curve functionality. Currently, it specifies the hash encode twice implementation, which is effectively map to curve twice by taking the hashes, or given your input, hash it twice, hash it to the base curve twice using two different hash functions, H0 and H1 in this particular case, and then map to curve each of those values and then add them together. And the output is something indistinguishable from a random point in the curve. We are currently considering replacing with the hash encode base point technique, which, as you can tell, requires less map to curve functionality or computations, one instead of two. And it also works for, and we believe it works for all of the curves and the algorithms in consideration. In particular, the hash encode twice, we're not entirely sure if it works for Alligator 2, but we have it's pretty easy to prove that it does. The hash encode base point functionality does work for Alligator 2, which is something we really want to support. Moving on. So the recommendation table looks something like so. You have various applications you might want to run, or in this particular case, we just cited various papers which have protocols that you might want to implement. The requirement therein for these particular applications, and then some additional details about the curves or the particular application, like whether or not the curve is pairing friendly or works with a pairing friendly curve or a super singular curve and so on. And then we also have a secondary table which lists for each curve and for each of the requirements, be it an injective encoding, like map to curve or hash to curve random oracle, which specific algorithm you should use, and a pointer or forward pointer to that particular, algorithm in the document. So as an example, if you wanted to implement a PAKE from the BMP 2000 paper on P256, which requires a random oracle, we recommend you'd end up using the hash to curve functionality with SWU, because that works for any curve, and P256 being the one. Like I said, we can potentially change this recommendation later on, depending on what all the cryptographers tell us. So we are more than welcome to take, or more than happy to take suggestions on that particular front. And like I said, again, we added HackSpec because we want to drive it forward. We think it's good, and the implementations ended up being pretty concise and pretty clear. I mean, you can reason about them mathematically, and it's essentially just pretty straightforward Python code that you can compile out to C or whatever else you want, and it's good. And comments welcome on that as well. There are currently a number of outstanding issues that in the document itself, and I'm sure other people have some issues that may or may not have been raised. So the first one in particular is adding support for pairing-friendly curves. There's an open pull request to do this. We just haven't gone through and actually verified that the algorithm specified is correct. It references the paper, and it's in my queue to actually read the paper and get through this. This was raised last time as something that would be good, because pairing-friendly pairing-based crypto rather is becoming more and more popular these days. So why not have support, or at least a way to do this for those particular applications? Another item is, oh, that's you. Okay. Writing the cost comparison table, which, breaks down the efficiency or the computational complexity of each particular algorithm. And so if you're an implementer, you can sort of weigh the pros and cons and choose one that fits your needs, provided that, meets the particular requirements that are outlined in the tables above or at the beginning of the document. And there's also an open item to write the curve transformation function. So most of the algorithms assume like the point that you're hashing to is represented in an affine coordinate with an x and y value, but you might want some map to Jacobian coordinate or what other representation you want. And so we just need to sort of write that down, as that's an implementation detail that might matter for a particular application. So there are some open questions I'm hopeful that the research group can help us address. In particular, what generic hash to curve construction should we select? I alluded to the two we're using earlier. The first is the hash encode twice, and the one that we're potentially leading towards is the hash encode base point, which does work for all the curves specified. If you've read the document, I'd like to know, or we would like to know, if the structure can be improved at all for usability, for readability, for whatever ility you like. And then a sort of open question is whether or not it's even appropriate to include hackspec in a document of this particular nature. This is an experiment. We're trying to see if people are in favor of it, and I cannot tell based on looking out if this is a good thing or not. Please nod your head or shake your head. Or so yeah, like I said, any feedback on that particular issue would be very welcome. Our rationale for including it is that if you wanted to go and just quickly test it out, here's some implementation you can quickly grab. And if you want to run it, like your application is built in C, you compile it to C and you have it. You don't have to actually spend the time to go through and get it wrong. And it also serves as a very concise reference implementation for people who want to verify their own customized implementation or their own optimized implementation, what have you. And it has all sorts of nice cryptographic properties about the generated code. So that's nice. That is it. Are there any questions? Nope. All right. Maybe one.
Hi, Stephen Farrell. Historically, Cfrg documents that have any options generate tremendous confusion later on. Is it your intention to try and get rid of all of the optional things and just have one thing?
It's unclear right now. Ideally, we have, for each curve and for each, type of requirement, be it a deterministic encoding or a hash curve, there's one variant, and that's what everyone shall use. And whether or not we keep, the other permutations and combinations of the document is, unclear to us at this time. I think we're including them all because as we flush it out and, move it forward towards publication, we want to make sure we survey the design space as exhaustively as possible. But yeah, if the precedent is that you have exactly, or the right thing to do is to include exactly one option, so there is no selection that can be done. Good, yeah, okay. Noted.
Rob Austin, just one bit of feedback to your third point. So long as it's clearly labeled that in case of a conflict between the specification and the example, the specification wins, obviously, but so long as you're clear about that, I think actually having the reference implementation there, if it fits, is a good idea.
Great, okay.
I'm all about reference implementations, so.
Thank you, and that's good feedback. I think that's good. Sure. All right, thank you. Thanks, everyone.
Good evening, good afternoon. I'm Leo Raisin, Boston University. I'm going to talk about the updates to the VRF draft and mostly ask for feedback on various issues that are outstanding. So just a very quick intro. What's a verifiable random function? It's like a hash function, but with a public key and a secret key. The hasher has the secret key. The verifiers have the public key. So the verifier provides an input to the hasher. The hash using a secret key can provide a proof to the verifier. What does this proof do? The proof allows the verifier to do two things. One is convert this proof to an actual hash output using a proof to hash function, and the other is to check that this was the correct output using the verify function. Okay, so it's like a hash in that even if the hash share is adversarial, there's only one possible output. It's unique and it's collision resistant. But without the whole verification thing, the verifier cannot actually know what the hash will be. So it's in a sense like a secret key hash. So the verifier, if the verifier just gets the hash without the proof, will not be able to tell if the hash is right or wrong. In fact, it'll look entirely random to the verifier. There's a variety of applications I won't talk about, but that's where we are. And specifically, I want to talk about updates to the elliptic curve VRF in the draft. It's gone through an iteration. So how does it work? The first thing we do is hash to curve, as the previous talk talked about. So we hash to curve. Then what do we do after hash to curve? We actually construct a proof of three things. This hash value raised to the secret key, and a couple of helper values, C and S, that I'll talk about in a second. What is the output of the whole thing? The proof to hash just takes this h to the x value and outputs it. So how do you know that this is the correct hash? You know it because the prover will prove to you that it has the correct exponent, that h was raised to the correct x, or x is the secret key. So you're going to prove equality of two discrete logs. How do you do that? There's a bunch of algebra which I won't go into, but it's essentially the same as Schnorr signatures or EDDSA if you're more familiar with that. So you generate a nonce, and we've specified deterministic nonce generation. It should be a pseudo-random nonce, essentially. You compute some hashing, and you get some algebra, and then the verifier does some algebra, does the hash to curve of the input, and then does the verification. Okay, so the takeaways are that we have hash to curve and we have nonce generation, and we can talk about those for this talk. Some features, so the values h to the x is a curve point, so it's going to be like 256 bits. S is mod the field, so it's going to be 256 bits. C is short because collision resistance is not needed, it's only 128 bits. So this is useful for short applications where space is an issue. We added future proofing, so the first thing we hash is the cipher suite ID, so that if cipher suites change, we can update the cipher suite ID and not have weird hash input collisions where the same input represents the different things. This was a problem in RFC 8032, the EDDSI RFC, where they had to do funny things in order to avoid hash input collisions. What has changed since the last iteration? We added a new nonce generation. It's deterministic. And for the P256 NIST curve, it's identical to the ECDSA deterministic draft, RFC 6979. So now we have deterministic nonce generation in there. The hash to curve in this cipher suite, the P256 curve, is just try and increment. You hash, you hope you got a curve point. If not, you increment the counter, you hash again, you hope you get a curve point. We have a cipher suite with curve 2559, 25519, which looks a lot like EDDSA in many ways. Nonce generation is deterministic based on EDDSA. The hash function used is SHA-512. And then this cipher suite sort of has two variants. One variant where hash to curve is just try and increment. You try, you hope you get a curve point. And the other one is alligator squared, which is a time invariant way to do hash to curve. What we've added is domain separation to make sure that hashing is used all over the place in this thing. If you look at just at the design, and we want to make sure that two inputs to the hash, different hashes for different purposes, are never the same. Because if you have an input hash collision, you get an output hash collision, and that can cause all kinds of problems. And the way we're going to do it is two things. One, we prepend the cipher suite everywhere, and two, we just have a byte that tells you which use of the hash this is, 1, 2, or 3. We do that everywhere except nonce generation. We cannot add it to nonce generation if we want to be the same as other standards because they don't have it. But nonce generation is not an issue because it uses a secret that's not used anywhere else. So the adversary can't make it collide with anything else. A decision that we've made, but if people really disagree, we want to hear about it, is that we do not do something called pre-hashing. So 8032 EDDSA RFC does pre-hashing. If you have a really long message, you first hash it and then you do everything on the hash value. The reason they need to do it is because the message participates in the process in more than one place. So if it's a long message, you're going to have to chew through it more than once. We don't have this problem because the hash to curve, the H that you see on your left, already acts as a prehash. Everything else is based on H, not based on the input. This is the only place where the input goes into the scheme. So once we have that, it doesn't seem to make sense to do on top of that a prehash, right? So that's essentially the design of prehash. EDGSA does not have a hash to curve step, so it doesn't get to take advantage of this. We do. So we don't have a prehash. We have, as I said, 3 cipher suites, one with NIST P256 curve and 2 with ED25519 curve 25519. It's not clear that we need 2 25519 cipher suites. One has the hash to curve, which is try and increment, and the other has alligator. We're not sure we need to keep it. We can kill it. We're seeking feedback on that. We're seeking feedback also on nonce generation. So with the nonce in these schemes is very important. If you don't have a random nonce, you're in a lot of trouble. Your secret key can leak. It's been sort of relative consensus of the community that the way to do it is to have pseudo-random nonce generation. The question is exactly how. What RFC 8032 does, it has 3 options. And the reason it has 3 options is because it has pre-hashing and or context. And the options are here on the screen. The second and the third are kind of weird because they're trying to avoid essentially to create domain separation. We did something similar to RFC 8032, but not identical because they have an input and we have the hash to curve of the input in there. Now switching back to the NIST curve, the way deterministic ECDSA RFC 6979 does it is by using an HMAC DRBG that requires 10 applications of a hash function to get a nonce. It's not clear that's the best way to do it, and it's subject to a tiny probability of a timing attack because if you don't get nonce in the right range, you redo. And alternative is to use SHA-512, but the suite doesn't have SHA-512 in it. It's only based on SHA-256. Do we add that? And so that's a decision to be made. Do we really want the 10 applications of SHA-256? Also seeking feedback on various minor nits, we use exponential notation, h to the x, because that's how groups are written. Do you want elliptic curve notation, x times h? What's better? Do people want support of contexts? A context is something like a message, but not a message. RFC 8032 has that. We do not. Minor nits, what's the best terminology for take a hash and then take a few bytes of it? First octets, last octets, leftmost, rightmost, what do people prefer? And if people like the way we did domain separation, for this VRF, the draft specifies one more VRF, which is RSA based. We will do domain separation the same way if people like it. So I think that's all I got.
Thank you very much, Leonid. Stanislav Smyshlev, Crypto Pro. Thank you very much for this work. I really think that's very interesting and necessary work. And the draft has significantly improved since London. Now there is much more clear section about secrecy of input against dictionary attacks. I like new formulations very much. And the question I have is, if I understand correctly, the VRF notions of security are in some sense more strict than for deterministic signatures. And for signatures, we do have at least 2 good constructions that have quantum resistance. It's XMSS and LMS constructions. Have you thought or have you seen any ideas of how to move these ideas of hash-based signatures to VRFs? It seems that such a way can exist, and do you know such works, or maybe have you thought about it?
So I haven't thought about it. I don't know about it. I know some people who've been thinking in lattice-based VRFs, but I don't know of any results. I just know that people have been thinking about it. Thank you for the question.
I underline hash-based signatures because for hash-based signatures, we do have good security proofs, and for lattices, we do have some potential issues with them. So maybe we should think about hash-based.
Definitely a worthwhile project, yes.
Okay. Thank you.
Yes.
Chris Wood, yeah, thanks for the talk. This was great. Just a quick question regarding the new hash to curve stuff that you've added. To Stephen's point, or question during my talk, it would be great if we could somehow converge on whatever we happen to choose in this document or next, because otherwise we'd have two competing hash to curve implementations or algorithms in two different documents, which would cause much confusion, I think. It would not be advisable.
So
I don't know how you want to do that.
So I think somewhat it's a question of timing because there are dependencies on this VRF draft that need to happen. But we have flexibility because we have Cypher suites. And so one way to do it is whatever the hash to curve draft converges on, change that into a Cypher suite.
Okay.
That's probably the approach that simply because of the dependencies that are there.
We can talk more.
Yeah, I'm happy to talk afterwards.
Yeah, thanks.
Thanks.
So just reading from Jabber from Dan Harkins, he says, is it possible to make this generic and plug in any curve and have a hash algorithm depend on the size of the curve's prime?
Yes, it's possible to make it generic, and the description is somewhat generic, but it's not fully generic right now, and you instantiate it with Cypher suites, but for specific curves, you'd have to do different things a little bit.
Chris, again, real quick question. I noticed in the draft that there's an outstanding to do to add potentially more general hash to curve implementations. Are you just going to remove that or axe that in order to move forward?
I think it depends on the timing. Yeah, so if we, moving forward, in terms of getting working Cypher suites seems important, but also adding. So I think we may, I don't know the answer yet.
Sure. Yeah. Okay. Thanks.
Hi, Robin Wilton. This is probably the least cryptographic intervention of the afternoon. For your question 3 there about first n octets, last n octets, would it work to specify an offset and the number of octets? So as long as you're sure you're not going to overrun the end of the hash value, that would allow you to specify different offsets while still using
sure, right. It's just the question of what is more convenient for implementation. Do you want to take 0 through 32 or 33 through 64? And how do we specify it to make it clear and all the sort of concerns about little endian and big endian so that people don't get confused about which ones? It's more of a language issue than anything else.
Again, one more question. Earlier, Sharon spoke about some applications like Algorand application of VRFs. Maybe do you have any new applications that could be interesting to illustrate the technology? Because I think the main questions about VRFs are applications, because it's a new kind of primitive, kind of new. And Algorand is a good example of application where it is really applicable. Do you have any new examples?
So VRFs are already being used in key transparency projects and Connex, that sort of thing. They actually implemented and used. There's a signal implementation of VRFs. You're right that Algorand and also possibly Ouroboros is using it, and also NSEC5, which is a DNSSEC piece, is also using VRFs or wanting to use VRFs.
Yes, thank you. And I'll be happy to provide a security review when you will be ready to finish drafts. Thank you very much.
Thank you.
Stanislav, you're next.
Thank you very much. Stanislav Smishlev, CryptoPro, and I'm presenting a joint work with Cass Kramers, Lou Garrett, Nick Sullivan, and Christopher Wood. The work is randomness improvements for security protocols. This draft was adopted as Cfrg draft at London meeting at IETF 101. And I'll do a status update about this document, and I'll outline the questions that we have now. A short overview. So basically, the motivation is kind of obvious. Most security protocols rely on 100% good entropy, and in real world, PRNG can fail, can break because of bug, because of backdoors. All of us know the example. Because of hardware failures of the entropy sources that are used to feed the initial state of PRNG, and system entropy pool, if it's joined, can be impacted by the attacker. So developers all over the world use some ad hoc solutions to support their PRNGs, to have some safety net, and the motivation of our draft is to prepare a good solution with quite a good analysis that can be used in a majority of applications that need such a backup. The idea is based on Nexus-Trig. So the idea is very simple: to mix in the private key, if you have one, in some secure way. And this idea has a lot of issues and problems, both technical problems, both security problems. So the way how to mix them in is quite tricky, and we try to understand how to do it better. So we try to consider associated issues, and most of them are outlined in the previous versions of the draft, and we hope to find a solution such that any call for entropy can be replaced with this one. So the construction as it is now in the current version of the draft, it has changed slightly. So that G is the output of some CSP RNG, and in our construction, we change it, we replace it with the mixing in with signatures calculated with some secret key with a tag 1, which is unique and environment specific string. And all of this is mixed in with function extract, which is basically a PRF or KDF, and then expanded using tag 2, which is basically nonce, to the output X. Tag 1 here is a constant string, which is specific for device and protocol or an environment, and tag 2 is a nonce, actually, that can include a timestamp of counter. That must be unique. The changes from the previous version are the following. First of all is the construction itself. It has been generalized, so now it has the output lengths of n of the same lengths as for initial CSP-RNG. So it's based on HKDF notions of extract and expand. Moreover, we think about fixing the construction from HKDF RFC. And we added some clarifications about security considerations about tag 1 and tag 2, and David McGrew, in his recent opinion about the document, has mentioned that we should stress something about tag 1 more explicitly, and we'll do that. So, namely, tag 1 is a countermeasure against many possible vectors of attacks, including that follow from cloning virtual environments or several machines using one HSM with one secret key, and we'll try to clarify this point in the draft more explicitly. And tag 2 is a timestamp that ensures that outputs are unique. We thought that it will be reasonable to define target security properties of our construction. First two of these properties are the properties that guarantee that replacement of any CSP-RNG with our construction won't do any harm, so it won't be worse, at least. So first of all, that if CSP-RNG works fine in some security model, then the output of this construction will be good in the same security model. Secondly, we don't harm the private key. So we don't increase the probability of compromise of our private key, maybe only for some negligible advantage. And the third property, our aim and our meaning of using this construction, that if Cfrg is broken or even controlled by adversary, or even just degenerates to constant string, then the output of the proposed construction will remain indistinguishable in corresponding security model. We relaxed requirements for signature scheme. They were very strict. They required that the scheme is deterministic, and actually it doesn't need to be deterministic. It just needs to use its own entropy source. Why we thought that this relaxation is needed? Because if you use HSM with its own internal entropy source, then it's okay. The problem is only when you use the signature scheme, which is not deterministic, that uses the same entropy source as we're trying to page. So this clarification was added to the document. Some minor issues based on one of our opinions in the list were added about the comparison to RFC 6979. Actually, the construction can look more or less comparable to the construction from RFC 6979, but it has completely different semantics and meaning. For example, if you have an HSM with a private key used inside of it, then the construction of 6979 it can be implemented inside the HSM, and our construction uses it from outside, so uses calls to that HSM. The stated plans. Actually, I thank David McGrew for his today's message to the list, because it reflects most of our current plans. So first of all, we must obtain up-to-date security assessment, because the ones we have are a little outdated, and we should add more specifications to the draft, specify our construction, and add recommendations. Some of them were already in the slides, and some of them are the same that was in the McGrew's letter, and we think that we should add these clarifications to the document itself. And we should refine security considerations more to be stated explicitly, so that we can cover most of situations that we are aware about, which can lead to bad usage of this construction. So our reason and our aim is to provide constructions that will close a lot of possible gaps, and of course we want to close as many of them as we can. And we hope to get a new version addressing these issues until Bangkok. Thank you very much. Thank you for your attention. Questions, comments?
Thank you for the document and the presentation. David McGrew, Cisco. So I have a question just to informally talk it through. So one of the assumptions in the security analysis is that the signature of tag 1 isn't obtainable by an adversary, but the conventional security model for a digital signature is you can assume the attacker can obtain signatures for chosen messages. So there's some, I think you just need to explicitly state that as another case in your case analysis and say, well, if your PRNG is no good and the attacker can do a chosen message attack, well, you your game is up, but it would have been anyway, or something like that.
Yes, I definitely agree with you, and yes, we should add this explicitly. Moreover, it was one of the issues that we tried to address as well as possible. We had a discussion with our co-authors about how this tag 1 should be chosen in a way that it can't collide in real world with plain texts that are signed. Of course, it can be it may not be fully formal, but of course we should add our these words to security considerations, and we'll do that. And thank you very much for the attention to this issue. This is really important, and in fact, we should add some more text about that. This construction is still good if these conditions are satisfied, and it breaks completely if any one of them is not satisfied. Yes, we will do that. Thank you very much for the comment.
Great, thanks.
More questions? Thank you.
Would you like to try yourself because you're from PowerPoint? I'm not sure whether. Yeah, I pushed this one on the screen. I don't know if that's. Is the present button? Try facing. Oh, yeah. So what's what would be that? If you want, I can just do it. Okay. All right.
Good afternoon. I'm Hugo Kravchik. I'm going to present about this protocol we call opaque. It's an PAKE, a password authenticated key exchange, an asymmetric one in the sense that it's not two friends that share a password. It's a client and a server. The client has a password, or the user has a password. The server keeps a image of that password. This is based on recent work that we presented in Eurocrypt 2018, and I've written a draft about this, which I will submit officially. Right now, a week ago or something like this, I sent an email to the message to the list with a pointer to a write-up of this draft. Again, I'll do it. I'll submit it officially. Can you? The next one. Okay, so an asymmetric PAKE, the requirements are first that it will be PKI free, not to be based on PKI, not like, for example, the current practice of sending a password over TLS that depends on the security of PKI. So we don't want that. And the other thing that we want is that the server will never see the password. The only way for the server to learn about the password of the user is to run an offline dictionary attack, something that is unavoidable once you have the image of the password under some one-way function. So compared to TLS, in TLS, the server sees the password when it decrypts the TLS. And of course, there are all kind of other points where the password is visible in any termination point, middle boxes. But TLS does, I mean, the password over TLS does one good thing, which is it uses secret salt for the hashes, which makes the work of the attacker as hard as possible, meaning that at the only point in which the attacker can start running an offline and a dictionary attack, an exhaustive dictionary attack, is only when it breaks into the server. Now, since APEC has all these requirements and doesn't need a PKI, you would assume that all these APECs, by the way, A is for asymmetric or augmented, both terminologies are used. So you would assume that APECs are always better than TLS, password over TLS, but maybe the next one. This is not the case. It's kind of surprising, but all APEC protocols known to this date, those that are, the practical ones, the impractical ones, the proven ones, the unproven ones, none of them can actually use secret salt in the hashing. So either they don't use a secret salt, either they don't use salt at all, or if they use salt, they have to transmit it in the clear from server to the user. And again, that is common to all the APECs that you have heard about, like SRP, SPAKE2+, OCPAKE, and any of these protocols. Next. So you could think that maybe there is something inherent here, that, for example, if you want to do a PKI-free APEC, then there is no way you can also do secret salt. And the answer is, and this is not the case. The next one. And this is what we actually show in this protocol, is the first one to be secure against precomputation. So if you don't use salt, as we all know, then you can build a universal dictionary before you break into the server. If you use salt, but the salt is known to the attacker, then at least the attacker can build targeted dictionaries against a user, and immediately when it breaks into the server, it can find the password. So opaque will have the property that this is not possible. It is secure against precomputation, and also is a formal proof of security under a strong definition. I didn't say that it was written there, but it's important to note that there were provable or proven PAKE protocols under crypto formal models, and even those were not secure in this sense. And that's because these models actually allowed for pre-computation attacks, which basically goes against the very basis of, or the very, basic requirement that you would like to have in these protocols. Okay, so opaque is built on the basis of this primitive called oblivious PRF, oblivious pseudo-random function. What's an oblivious pseudo-random function? So a pseudo-random function, we all know it's a function that if you don't have the key to, you don't know the key to the function, then it behaves like a random function, indistinguishable from a random function. What's an oblivious PRF? An oblivious PRF is a PRF with a protocol between a client and the server. The server has a key to the PRF. The client has an input to the PRF. At the end of the protocol, the client learns the value of the function on this point, on the X, which is the input of the client, while the server does not learn anything. It doesn't learn about the input of the user and doesn't learn anything about the output. So it generates the output, but doesn't learn anything about it. Okay? And this is going to be very, very useful in this case. So again, PRF is an interactive PRF service that returns PRF results under the key that the server has, but the server does not learn the input or output of the function. Next one. So the idea of opaque is very natural. Once you think about an oblivious PRF, what you're going to do is that the user will take the password, PWD, and will exchange it for a strong key produced by the OPRF. Now, since the server can provide the value of a PRF on the password without learning the password or the output, then basically the user gets, in some magic way, it replaces its password, its low entropy password, with a strong key, where the entropy comes from the key, from the OPRF key at the server, but again, without the server learning anything, not about the password and not about the key that was returned by the OPRF. So now the user has a strong key, and now everything is simple. What the user will do, it will store at the server an encryption of a strong private key, will retrieve during login the private key from the server, decrypt it using the output of the OPRF, and now server and user or client can run the key exchange with the regular private key for the user, private key for the server. So essentially what this does is give you a compiler, a transformation from any key exchange to an asymmetric PEIC. And this compiler, since it's very, very general, actually will give us flexibility in choosing what is the best key exchange protocol that we want to use in a given situation. Next one. So here I'm showing one implementation of an OPRF. This is just blinded Diffie-Hellman, a very simple transform. I will not get into the details of the function. Again, it's simple, but I don't have time. I want to highlight the performance issue. Here, the server requires one exponentiation for the server. For the client, is one fixed base exponentiation and one variable base exponentiation. And this is just a single round. Message from client to server and from server to client. There is also, I should have highlighted it, there is here, this h prime x to the k is actually hashing into a group, into a curve. Next one. Now, here you see these two values. Okay, these are exactly the OPRF based on Diffie-Hellman. G to the x, G to the y are the key exchange. These two messages, actually, if you have an implicitly authenticated key exchange like HMQV, you can, this is the whole protocol, what you see there. Just one message each direction. If you want explicit authentication from the client, then you add one more message. Next one. Again, this is very fast, and just to give you an idea, of course, the details need to be read more carefully, but this is just to give you the general idea. The cost that you have is the key exchange cost plus the OPRF cost, which, as I said, is one server exponentiation, two for the client. If you use opaque with HMQV, which is a very efficient implicitly authenticated key exchange, then you basically get the full protocol, the full opaque in 2.5 exponentiations for each party. This is more or less similar to SPAKE2+, which is one protocol that has been or is being proposed exactly for this functionality. The difference is that SPAKE2+ is insecure against pre-computation attacks, because it cannot use secret salt. And also, SPAKE2+ does not have a proof. The draft that defines SPAKE2+ says that there is a proof, but no, there is no proof. It was proposed in a paper by David Cash and Victor Shoup and John Kamenisch. But I checked with the authors. The paper doesn't have a proof, and they don't have a proof. There is not even a model in that paper. But maybe more essential is the fact that that protocol cannot accommodate secret salt, and opaque can. By the way, I'm using HMQV as an example, and I have to say that since HMQV has a patent under my name, even though it doesn't belong to me. But what I do want to say is that if there will be interest at some point of standardizing opaque with HMQV, then most probably that will not be an obstacle. I cannot promise, but I think that's what will happen. Now, what I think is most important in these asymmetric peaks is to find ways of integrating it in TLS, because of these things that opaque is actually a compiler from any key exchange to an APEC. It means that it's very easy to integrate it with TLS. All you're going to do, you're going to use the OPRF to exchange the user's password for a signature key, okay? And now you can use that signature key as a client authentication in TLS. If you don't care about encrypting the user ID, you know, when you contact the server, then you could do the whole thing exactly in the same 3 flights of a regular TLS. If you want to encrypt the account information, then you either need to use a resumption key if you have it, or you need to add one round trip to TLS. But again, everything is very easy to integrate because of this just general paradigm of take my password, give me a key, and now I can do with that key whatever I want. Next one. So OPEC security, it has been shown to be secure against pre-computation attacks and is PKI free. It has forward security, and something I didn't mention, you can make it harder by doing iterated hashing, as we usually do in regular password protocols. And these hash iterations are actually offloaded to the client. Next one. So to summarize, opaque offers an asymmetric peak that is efficient, probably secure, does not rely on PKI. The server never sees the password. Actually, even at registration time, the server does not have to see the password. It uses private salt against pre-computation attacks, uses hash iterations on the user or client side. It's friendly to TLS integration. And 2 things I didn't mention is, since the user is actually storing its private key with the server, you can use exactly the same mechanism to store other secrets, you know, your Bitcoin key if you want, or any credential or anything that you want to store at the server. And finally, if you want to make your server even more secure, you can make it into a threshold, you know, like 2 out of 3 that you have to break into 2 servers before you can even start running a dictionary attack. Last one. So if we are looking for a strong asymmetric peak to standardize, are we? Then OPEC seems to be a very good fit, particularly if we want to integrate with TLS 1.3. It is not clear to me what is really the sentiment with respect to really building something like this into TLS 1.3. This is much more secure than the password protocols that we use now. It has even some advantages. In particular, it's while now what we are doing is protecting passwords with TLS, doing something like this protects TLS against PKI failures. So there is some very valuable this value here. So if people are interested in pursuing this, please let me know, and we will try to build this something more detailed for actual implementation.
Okay, we're a few minutes over time, but very quick questions. Yes.
All right. Yeah, Chris Wood, Apple. Thanks for bringing this. This is really great. I definitely want to see this happening in the CFRG. 2 quick questions. Number 1, The OPRF that you specify, is that the same like 2-hash Diffie-Hellman OPRF that you and Staj use in the password protected wallets paper, or has that changed?
The only change in the specification here is in the paper we use exponential blinding, and here we use multiplicative blinding.
Okay.
And there's some technical issues there that
is it detailed in the opaque
we
paper?
can talk about.
Yeah, we'll talk about it later.
Yeah.
Okay. Second question. You mentioned the compiler works for any key exchange protocol. That really means
Yeah, so
absolutely any key
to be
exchange
precise, it's not every key exchange, it's every key exchange protocol with the KCI property, okay, which is most protocols, and protocols that don't have KCI, you shouldn't use them in the first place.
Yes.
So it's a technical issue, but it's significant. There are several technical issues here that show how sensitive the thing is to, and the proofs actually show you what you need.
Yeah, and then the third one, really quick. There is an existing draft in the TLS working group on integrating generic PAKes into TLS 1.3 that Richard Barnes is driving. I don't know if you've spoken with him at all about it.
No, I haven't.
Okay.
I want to anyway. I want to talk to Richard Barnes. So whoever sees him, tell him that I want to talk to him.
We know where he lives. No.
I thought he will be here, but I was told that he has some conflict. Yeah. His priorities.
Stanislas Mishlev, thank you very much for bringing this. I really think that's very important work. Just a small clarification. If I understand correctly, that we can modify any KCI secure key agreement to the password authenticated key agreement with migrating our private key to the server in encrypted way. But if an adversary has a full access to the server, occasionally it cannot mount only dictionary attack on the password, but also on the private key itself. So if I understand correctly, that we should not use the same private keys for different servers in this case if you don't believe, you don't trust any one of the servers. So if one of the servers is compromised, then not only our password is known.
Yeah, there is no reason to use the same private key, because you don't have to remember it. You just get it from the server. So it's not that you're keeping it somewhere or something.
Of course,
the user starts from no memory. He only knows the password.
Yes, if we start with opaque as a complete protocol, of course. But if we treat this or think of this as of the way of moving from our private key authentication to the opaque authentication, that can be a mistake of reusage of private keys. And that
if you use it to store credentials, then you are trusting that server, or at least, I mean, if your password is strong enough, this is not going to be found. But okay.
Thank you very much.
Bob Moskowitz, HD Consulting. Hugo, the link that I just tried did not work to get your draft.
Say that again.
I just tried the link for your draft, and I got an error.
Okay.
So PDF works. Oh, okay. The text doesn't work.
Oh, the text doesn't work. Okay. Thank you.
Hi, David McGrew, Cisco. So, Hugo, this is really good stuff. Thanks for doing it. Thanks for bringing it here. And I'm sure Richard Barnes will be interested to talk to you more about that. So I just wanted to encourage you to keep this up. And I want to say there's let's see, a way to use passwords to authenticate to servers such that you don't have to trust the server would be really meaningful, because of it's very commonplace nowadays for phishing attacks to steal people's passwords, right? That would be a really meaningful improvement in the security of the internet if we could eliminate that trust in the server.
Yeah. By the way, there are new in the last slide. Oh, actually, I mentioned here some new tools that are for password. If we use everything we know, the state of the art, which is very practical with passwords, password would be much less insecure than they are now. I mean, still the password 1, 2, 3, 4, 5, 6 will be insecure, but.
Yeah, we need to be careful to make sure that we don't bring all the problems of passwords into any future designs. But but it's sure worth doing.
Sort of a nitpicky comment. So there are 3 drafts presented today. They're all elliptic curve drafts. We're all taking things to the exponent, hashing to the curve, and doing things. So we've all written things a little bit differently. If you look at like the way that our draft, the VRF draft. By the way, I'm Sharon Goldberg. I'm one of the co-authors of the VRF draft that was presented before. The way we've written it and the way you've written it, they're pretty different. So we should probably try to make the notation consistent because the actual operations are not the same, but they're very similar. It's the same set of things. So we should try to converge also with you guys on like, how do we write this in Cfrg? And let's just, nail it down and be done. So we don't have to keep having different.
Yeah, I agree.
Speaking from one of the co-chairs, I just reviewed 3 drafts and they all use different notations as well. And, it's sort of hard to make people rewrite it to be the same. But, I encourage this sort of collaboration. Of course, yours is the right one, yes.
Thank you. Okay, thank you.
Yes. Right. Okay.
Hello everyone, I'm Benoît Viguier from Radboud University in the Netherlands. I'm going to quickly make a quick update about why we should actually pick Kangaroo 12 as an RFC. So Kangaroo 12 is an interesting function because, well, it supports arbitrary output length, so you can actually use to derive entropy from a source with 128 bits of security. And there is no RFC that provides such functionality so far. It also provides hashing with parallelism, a scalable parallelism, which means that if your input length grows, then the degree of parallelism that you can use is actually increasing. And you don't have to specify specific parameters like I want to use this function with, I don't know, a degree of parameters of parallelism when I am actually calling it. Also, it's based on the SHA-3 permutation. So Kangaroo 12 is a hash function or extendable function. It's not a construction with generic properties. It's really a hash function that you can use instead of SHA-3, for example. And it's based on SHA-3. So from that, we can reuse the code of Ketchak, reuse the V8 instruction that are currently implemented there. And also it's at least twice faster than SHA-3. And because it's based on SHA-3, well, yeah, then it's public design, and it's really have the same cryptanalysis of SHA-3. This means that we have at least 10 years of cryptanalysis on it, and that's about 35 papers that have been published on it, which is actually more than SHA-256 and SHA-512 papers, where we actually counted only 21 through ePrint and other sources. So it's really, really secure design and not just something that is new, because the construction is based on proof for the sponge construction, for the Sakura tree construction. So the parallelism is proven correct. The sponge construction is proven. And then you just rely on the security of SHA-3. So if you don't trust SHA-3, then you cannot trust Kangaroo 12. But I don't think this is the point here. Also, current best attacks are collision over 5 rounds for SHA-3. And we have string prediction over 8 rounds with a workload of 2 to the power 128. There is string prediction over 9 rounds with a workload of 2 to the power 256, but that's way above the security requirement that we want. And so we only have these 2 attacks over 5 and 8 rounds, and Kangaroo 12 has 12 rounds, so we still have a 100% security margin for the collision, and at least 50% of security margin for string prediction. So for that, it's still really, really secure and not just diminishing the security of SHA-3. So in the end, why is it interesting? Well, as previously said, it's an open design, result of a worldwide competition. It has a long-standing scrutiny from the crypto research groups from France and all over the world. It doubles the speed with respect to SHA-3. It has proven generic security, and the parallelism is actually scalable and not just limited to 8 cores or 4 cores. Thanks for your attention, and if you have questions.
Mr. Smishlev. Thank you. I have a short question. Now there is a process in ISO C27 of a new amendment on hash functions. Do you have any plans to bring in this to ISO? Because they just have the process of revision of hash functions now, and maybe it will be a good chance to bring new constructions there.
I didn't hear about that process, so I actually will have to take a look at it, and maybe it would be a good idea to try to have that in the ISO.
The process in ISO is continuous, but now there is a new amendment being prepared, and when you have a new amendment, you can discuss, and I hope that the time is not in the past of the deadline of adding new constructions, and maybe it's also a good way to go. But of course, in IETF, it's a good way to proceed also. Thank you very much.
Thank you very much.
Okay, thank you. Chairs will follow up with you. All right, thank you. I think that concludes Cfrg. Enjoy the social if you're going to the social. Enjoy other things if you're not. Thank you. It wasn't particularly hard, right? It wasn't particularly hard.